Hello and welcome to the virtual course, Build Your Own Data Logger. This course is a joint collaboration between FreakLabs and WILDLabs. In Module 3-1, we learned how to implement our own command line. In 3-2, we learned how to sense temperature and humidity using the DHT11 sensor. In 3-3, we learned about the analog to digital converter. In this lab, we're going to learn how to keep time using the real-time clock chip on the WildLogger. The real-time clock, or RTC, is an electronic timekeeping device in a system that serves multiple functions. The basic function is that it keeps track of time and the calendar. In data logging systems, it also serves to timestamp data to give it context and temporal information. Timestamping is especially useful if you have multiple systems logging data in different areas, since the timestamp can synchronize the data for comparison. Along with that, a real-time clock is the center of our power savings strategy. It has alarm and timer functions which can signal to the microcontroller that an event is supposed to occur. This comes in really handy when the system spends most of its time asleep, since the real-time clock can wake the system up to perform an action like reading a sensor and recording it to the SD card. Once the action is finished, it goes back to sleep until the next time the clock wakes it up. In order to maintain its time and date when there is no battery power, an RTC requires a backup battery. On the WildLogger system, you can see the large coin cell battery that will power the RTC when there's no power to the system. A battery like this can last a few years before it needs to be changed. When a real-time clock loses power completely, the calendar and time are lost, which we often consider a catastrophic failure. On a data logger, the timestamp can no longer be trusted and the data potentially loses its context. Another point of concern with real-time clocks is accuracy. A real-time clock will always be slightly off depending on the accuracy of its quartz crystal. This means that it'll either be too slow causing it to lose time or too fast causing it to gain time. Depending on how accurate you need your timing to be, a difference of a few seconds per month might be tolerable or even a few minutes. But if you're doing something like synchronizing a wake-up schedule with other devices to transmit data wirelessly, then it's important the clocks are synchronized as much as possible. This chart shows crystal accuracy versus temperature. Temperature is one of the main factors that will affect your real-time clock timing. Real-time clocks are driven by a periodic oscillating device, usually a quartz crystal, which it uses to keep time. Crystal accuracy is given in parts per million, or ppm, and the typical accuracy is 20 ppm for most watch crystals. This is true for the crystal on the WildLogger board as well. This means that for every 1 million seconds, it'll be off by 20 seconds. To put this in more familiar terms, 20 ppm accuracy means the clock will lose approximately 1 minute per month. So 40 ppm means you lose 2 minutes per month, and at 10 ppm, then you lose 30 seconds per month. Those are just some quick rules of thumb when you need to make calculations in your head. Timekeeping is actually quite a serious topic, and if we're locating devices outdoors, we need to consider how accurate we need our timekeeping to be. The reason is that the main factor affecting clock accuracy is temperature. The quartz crystal's nominal frequency is typically 32.768 kHz at 25 degrees Celsius and varies up to 20 ppm from about 5 to 45 degrees Celsius. The accuracy, or ppm, degrades further as the temperature goes outside of this range. For example, at minus 20 degrees C, a not uncommon nighttime temperature in many places in the winter, the crystal can get close to 80 ppm of inaccuracy. Likewise for 70 degrees Celsius, a common temperature inside a sealed enclosure exposed to the sun. For maintaining accuracy, there are various methods to compensate for these environmental factors. These could be software algorithms, crystals with temperature compensation built in, crystals kept in a temperature-controlled casing, GPS timing correction, and rubidium and cesium atomic clock compensation, where accuracy is of the utmost importance. Cesium atomic clocks are so accurate they're regularly used to measure the speed of light and were used to prove Einstein's theory of relativity. On a side note, they can sometimes be found on eBay for under $1,000. Rubidium atomic clocks can regularly be found on eBay for under $300, but that's a different topic. If you're interested in falling down a timekeeping accuracy rabbit hole, I recommend you check out leapsecond.com and the Time Nuts mailing list archives. In this submodule, we've learned a bit about real-time clocks, how they're used, their accuracy, and how environmental factors affect them. Now let's get into the lab portion of the submodule. Stay tuned for Module 3, Lab 4A.
Say kids, what time is it?